Joke. A malicious laugh. And of course, that's where we're starting the recording for everybody who wasn't here. They won't be on the joke. All right. At any rate, I'm sorry.
Thanks for the extra credit on the test.
Yeah. Well, if you didn't get that, then if you didn't get that comment, then it might be hard for you on the next one. So it's good that we had that recorded. Okay. To reiterate, the basis sets. We want to build up. We hit a few. We introduced basis sets and worked through an example for an even problem. One where we had removed a frequency and done something analogous to what an oscilloscope does. In terms of AC coupling. I'm trying to dust off some cobwebs because it was a whole week ago since we talked about it, and there was a test in between. But that, hopefully, I've refreshed your memories a little bit, although I know you've been thinking about other things in the meantime. So let's bring our heads back into the world of Fourier transforms. And we'll do that by illustrating an almost dizzying array of basis set transformations and theorems. And we're just basically today going to be focusing on building up this really robust toolkit of things we can mix and match for describing complicated functions and correspondingly their Fourier transforms. And my goal is hopefully to get through convolution today, because if we can do that, then that's really where one of the key strengths and values of Fourier transforms shines through to a great extent. Convolution shows up everywhere in instrumentation, and it turns out that convolution integrals are a real nightmare to evaluate, but they become much simpler through Fourier transform relationships. Okay, so theorems. We're going to hit, these are following the lecture notes. I forget which section this is, but it's the one labeled Theorems 1. So I'm going to follow this in order. So if you aren't here today, then you'll at least know what we covered, and you'll be able to use that as a reference, the lecture notes as a reference for this. So we have 4 theorems, and we've actually implicitly already used, I think, 2 of the 4. And the 4 theorems are scaling. I'm going to write them all down first, and then we'll sort of go through what each of them is and means and why it's a formal proof for why it actually works the way that it works. But that way you'll have it in your mind what the goal is before we go through the derivations. So the scaling theorem is a simple one. If I have if I have a Fourier transform pair F and phi, then AF equals A phi. Second one is addition. If F1 of t is a Fourier transform relationship with phi1 of f, and F2 of t also has a Fourier transform pair, then the sum is the sum of the 2 also Fourier transforms. Third one, similarity. Again, if we're starting out with a Fourier transform relationship between f and phi, am I writing too fast?
No.
Okay, good. Then f of a times t is 1 over a phi of f over a.
You're writing a little fast. Just a little.
Then I better move on. I only have one more. Power. Yeah, the power theorem. You have to say it that way too. It's a requirement. It's a complex conjugate. So the power theorem, well, is basically the integral over the magnitude of f of t for all times is equal to the integral over the Fourier transform in frequency domain over all frequencies. There's a question.
Why is it called the power theorem?
Yeah, the question is, why is it called the power theorem? Because if we think voltage versus time, right? Voltage goes up and down, and the average can often be zero if it's a sinusoid. But yet we still draw current in electronics, right? And what we draw is power, which is the squared magnitude of that voltage. So this is just saying that the power squared magnitude, right? The magnitude squared is in each of these, either in frequency or in time. The squared magnitude over all times is equal to the squared magnitude over all frequencies, which is basically saying I have some power draw that happened here in the time domain. That same power must also have existed in the frequency domain. Does that make sense? And that is going to be my entire formal proof for the power theorem, by the way. That was it. Pretty impressive, wasn't it? It's all very qualitative. The other three, I'll say something, I'll actually bother doing something with, I think. But the power theorem, I'm not going to bother proving. But hopefully it makes sense in terms of just, if you think electronics, it makes more sense than other things. But it also works for optics. We're measuring intensity as opposed to electric field. It's the same basic idea. Okay. And it makes sense intuitively that if you're talking from negative infinity to infinity, in either time or frequency, they should end up being the same thing, because it shouldn't matter if you're describing that power in the time domain or the frequency domain. You should get the same result either way. That's all that this theorem is stating. Okay, everyone has this written down? Okay, I'm going to go through. Yeah, please.
Is there a reason that we're doing an equal sign instead of interchangeability?
Yeah, you caught this. So you'll notice that in all of these other theorems, I have the double-sided arrow. The double-sided arrow means Fourier transform relationship. If I Fourier transform this, I get this. If I Fourier transform this, I get this. This is not a Fourier transform. This is simply stating that the integrated intensity in the frequency domain is equal to the integrated intensity in the time domain. That has nothing to do with the Fourier transform relationship. It's simply a theorem. It's not a Fourier transform pair, the way that these other three theorems are. It's a good point, though, because I could have easily just passed on by that if someone hadn't called me out on it. Okay. So let's convince ourselves of the validity of the scaling theorem. The scaling theorem is one we have implicitly already assumed, in fact, when we worked through our basis sets examples on Thursday of last week. So proof for the scaling theorem. I don't need that. I like the red. I'm going to go with a different color here. So the question is, what is the Fourier transform of A times f of t? Well, that is going to be the integral from negative infinity to infinity of A times f times e to the minus I 2 pi f t dt. That's the definition of the Fourier transform, right? right? And
Right.
3 people nod in unison. Yes, there we go. Someone said verbally. I like that. Some confidence out there. Why would you have any objection to the statement that this is the Fourier transform when I'm supposed to be telling you this in the first place? So yes, this is the Fourier transform from time to frequency. And because it's the time to frequency, we have the negative sign in the exponent. If I'm Fourier transforming from frequency to time, it will have a positive I in the exponent. And that's the only significant difference between a forward Fourier transform from time to frequency and a backward Fourier transform from frequency to time. Dusting off more cobwebs. All right. So if this is the Fourier transform, you can easily see that you can pull the constant out of the integral. Right? That's my proof. Pretty exciting, isn't it? There you go, we're done, right? Because then this now equals a times the integral from negative infinity to infinity of f of t e to the minus I 2 pi f t dt, which equals, by the definition of Fourier transforms, a times phi of f. Because if you look at this function, this is not a function of time. I'm integrating over time. The only thing that's left is the function of frequency. Yeah. Okay, yay! Scaling theorem done. Check that one off. Addition. Oh, shall I give people a chance to finish this up before moving on? If you're done, then feel free to use this time to work on your exam or something. Okay, we'll move on. The next one is the addition theorem. This one is almost as trivially easy as the last one. And that's basically, if I have 2 Fourier transform pairs, then the sum and the difference correspond to the sum and difference in the Fourier domain. So let's just do this. If I have f1 of t plus or minus f2 of t, and I Fourier transform that, then what does that look like? That's going to be the integral from negative infinity to infinity of if nothing else, these proofs are going to get you feeling very comfortable writing out the definition of the Fourier transform, because you're going to have this integral with e to the minus I 2 pi f t written over and over and over in your head, and hopefully on your paper as well. Don't try to write it directly on your head, though, by the way, because you run out of real estate there. I'm sorry, I'll move on. Everyone's a little sleep drunk. Okay. So if we have this integral, then you can carry this e to the negative I 2 pi f t into each of the 2 terms in the sum, right? So I can write this as the integral from negative infinity to infinity and you'll recall that the integral of a plus b, well, I won't even bother writing that because I have to add too many extra functions in there. I have an integral over a sum of 2 functions of t. So what can I do? I can do this. Right, as a sum of 2 integrals. You can separate out those 2 integrals. Which is now phi1 of f plus or minus phi2 of f. Very satisfying, isn't it? Yeah. Fourier transforms are easy. It's like the questions at the bridge of doom, bridge of death, Yes. Okay. On to the similarity theorem. And for those of you who didn't catch that reference, feel lucky. But with that being said, sheltered. It was a Monty Python reference. I'll move on. Okay, similarity theorem. That one's it requires a little bit of manipulation to understand. So that one is, just to remind you, the similarity theorem states that f of at Fourier transforms as 1 over the magnitude of a phi of f over a. So we're going to do it by defining t equals at. Oh, and this should be a capital F, just to be clear. And this is a lowercase f on the right. If I take the Fourier transform of f of big T, then it's going to be from negative infinity to infinity of e to the I 2 pi Now, just to keep things really clear, I'm going to use f, capital F, to have two different meanings in exactly the same equation. So let me apologize in advance and just resign myself to the fact that I did the exact same thing in the lecture notes. So for consistency, I'm going to make the same annoying substitution here as well. Capital F is really the frequency-dependent counterpart of little f, corresponding to big T. So if I have a little f, little t pair, I have a big F, big T pair. And so big F, I'm going to try and get rid of it as quickly as possible, but I'm going to leave it in there for a little bit of time just so I can do this substitution, okay? And if T equals A sub T, then F, big F, equals F over A. I think that's correct. Is that right? Big F equals little f over A. Yeah. Yeah.
So you said the one in the integral equals f times t?
This f, here's what I'll do. I'm going to make this f red. That way we can tell it apart. Actually, yeah, I'll do that. There. Does that help a bit? In here? Right here? Yeah, that is big F times big T, which are, it's this T and that F. And if you multiply them together, you can see that that's where that comes from. Okay, so what is the Fourier transform of this? Well, let's do some variable substitutions. We know we can substitute for big T and call that, we want to get this in terms of little a and little t, right? So if I write this in terms of little t, what does that look like? This is then going to be, now I'll switch back to blue, because I'm going to use little numbers. Negative infinity to infinity of f of at, e to the minus I 2 pi. Big F is f over a, and t is a times t, d capital T. How do I get rid of that capital T as the variable of integration? Well, I know that t is a times t, right? Big T equals a t. So dt equals a times dt. D big T equals a times d little t. So I can substitute that in here. Right?
And that's because A is a scalar?
Yep. It's because a is a scalar. So this becomes a times the integral of negative infinity to infinity of yeah. don't do that to me. It usually likes to delete some part of my proof when this happens too. Oh no, it kept it all. Yay. Okay. And this equals the Fourier transform of big F of big T. This is the Fourier transform of F of AT, right? You can see what's in there. So this is now phi of big F, and I'll substitute that as F over A. Because big F is little f over A. Does everyone see that step? Should I go ahead and I'll do it explicitly. This equals phi of F equals phi of F over A. You have a question? You know you want to ask it. You're just not sure if you should.
So why do we have X's value actually?
I don't know.
Why isn't it just A times phi of little f?
Because this I started out this whole thing, the Fourier transform of big T
Sorry, never mind.
equals the Fourier transform of big F, right? And then we just wanted to get rid of the big things and turn them into the little time and frequency components. So we wanted to undo that substitution we did initially.
Are we missing the 1 over A?
No, we are not. That's an excellent question. The question is, what about the 1 over A? Because if you go back to what we had, this doesn't look like that expression. Where's that 1 over A gone, right? And the answer is that the 1 over A is actually out here right now. We've moved it over in this equation. So what we have is A times F of AT is phi of F over A. And if we divide both sides by A, then we have the equation that we had before. Hopefully that makes sense. It's the proof. If you're comfortable taking things on faith, then I'm fine with that too. But I kind of like to see where things come from myself, personally. Except, of course, when it comes to the power theorem, which we will ignore. Okay. I see a few people still writing. I'll let you finish this up before we move on to some additional basis sets. We have 3 more to add and then some theorems to get through.